Hello there. Welcome back to the Ephemeris Podcast, the Astronomy Podcast. I'm your host, Aphelion, and thanks for being back. It's another Sunday, so we are going to continue the train of episodes on to Season 2, which is about cosmology. And in regards to a double episode week, because obviously I think it was a week or two ago that I missed one, I'm not sure when that's going to happen. Likely closer to holiday season when I have time to do more things and I'm not as busy. But that is besides the point today. Today's episode is about Galileo, and it was somewhat alluded to in the last episode, as I was talking about the reception of Kepler and how Galileo kind of worked with him. And so they're going to be on similar timelines, so it's definitely worth talking about Galileo, because let's be real, it's impossible to skip over someone as influential as that. So let's get into it. For the biography section in episodes going forward, I'm going to try and keep it a little shorter, because I've noticed that the biography sections are getting pretty long, and there's a lot of storytelling in recent episodes, and while it is necessary for people like Kepler, I'm not interested in extending towards that direction because we are focused on cosmological models and astronomical understanding. So yeah, just wanted to make that quick, what would you call it? You can't call it a footnote, but you guys get the idea. Galileo was born in Pisa in Tuscany, Italy in 1564. His father was a well-known musician and he was the eldest son. As for his education, in 1581 Galileo matriculated at the University of Pisa, where he began to study medicine, as I believe his father wanted him to study. And on this note, I must say it's kind of interesting to see that astronomy kind of pulls people from different backgrounds. Like, astronomy has captivated people who are going to become Catholic canons, which I think was Copernicus, and medicinal experts and mathematicians like Moslin and stuff like that. So yeah, I thought that was interesting, even though obviously medicine was kind of forced on him by his dad a little bit. That's an interesting fact nonetheless. Anyways, Galileo shifted from medicine to mathematics and Aristotelian philosophy, and he left college without a degree to teach mathematics in Florence and Siena. I believe there's some kind of financial precedent to him leaving college as well, but again, a bit besides the point. And he grew his credibility as a lecturer, and throughout his time lecturing, he began to encounter ideas like hydrostatics, center of gravity, and speed of falling objects, and that's going to become the essence of some of his early work. And in this process, Galileo began to abandon Aristotelian philosophy, the stuff that he learned, and resorting to Archimedean principles. But I think even that's going to change, really, because his work is going to accumulate to supporting the heliocentric model. So he's going to be in his own realm in that sense. But he started with Aristotelian stuff, he did some experiments, and then realized that's all wrong, and that's when the shift began to happen. So by 1609, Galileo had determined that the distance traveled by a free-falling object was proportional to the square of the elapsed time, and that the trajectory of projectiles are parabolic. And as we see that now, Galileo is correct on all of these points, but if you were to compare it to how they teach it in current high school physics, the distance traveled by free-falling objects is also affected by initial velocity in the appropriate direction, and maybe accounted for this and it's not actually mentioned, or it was just never considered, but that's just the way you'd learn it in high school physics today, and I just wanted to mention that. So to conclude, Galileo died in 1642, age 77, living the last 9 years in house arrest for charges of heresy for reasons we will discuss later. sort of after we talk about his work and we talk about more of his relationship with the church. So now let's transition into the work that Galileo did with his telescopes and how he transformed modern science. The first significant work of Galileo was in 1590, known as On Motion, which was followed by a lesser-known Mechanics, and both manuscripts were about the ideas presented in the Biography section, laws on motion and projectile motion, and that is self-explanatory. Between On Motion and Galileo's creation of his own telescope, he was mainly occupied with his tenure at the University of Padua and financial difficulties, so there's a big gap. But just a little explanation for why you have one work at 1590 and then he discovers the telescope like 20 years later. But anyways, once he discovered the work of Hans Hippershey, who was the actual inventor of the telescope, his endeavor to create a telescope began. Galileo learned about the existence of the spyglass and began to create his own lenses, and with the ones he grinded and polished, it achieved a magnification of 8 to 9 times, which I believe is 3 times better than any other one that had been created at the time. But an even better way to show you how significant that magnification is by telling you that most people at the time could only observe 6 stars in the Taurus cluster with naked eye. Galileo was able to see 35 of them with this telescope, and this led into his next work, the Starry Messenger. It became the first treatise to be published based on telescopic observation, and I think an impact that I left out in the notes that I will mention right here is the fact that Galileo kind of transformed the way that scientists approach science. For the last, I guess you could say 2,000 years, science was approached more on a philosophical standpoint and talking about more abstract ideas. But with the work that Galileo does that we're going to talk about here, he transforms, making scientific treatises from talking about abstract concepts to actually using mathematics to justify theories. So that's a really cool part about Galileo. So the Starry Messenger. It included the discussion of the Galilean moons, 4 moons of Jupiter's, and I believe the way that he discovered it was he was like, I see these 3 stars, quote unquote, that are next to Jupiter, but yet they seem to be moving with Jupiter, not quite fixed. And I believe from that information he was able to conclude that these quote-unquote stars are actually orbiting Jupiter. So yeah, and then 4th one comes along, 4 moons of Jupiter, Galilean moons, all good stuff. The Starry Messenger also included information about the moon's rough surface. With Aristotelian theory, it was believed that all celestial objects were perfect, and so the fact that Galileo could see rough spots on the moon kind of debunked that. And Galileo kind of talked about stars relative to planets in terms of appearance and proximity. Kind of the way that I talked about how he discovered the Galilean moons. So Galileo's next work, Letters on Sunspots, is quite self-explanatory. It's about sunspots, and it was another point against the perfection of the heavens proposed by Aristotle. He also published Discourse on Bodies in Water, where he explains that objects don't float in water because of their flatness, but their weight compared to the water it displaces. So pretty much he's just saying buoyancy depends on density, and that's exactly how we would explain it today. But there are some interesting claims that are made in this piece besides the buoyancy stuff. There's a couple of definitions that I'm going to pull out, and we're going to talk about it. So the first one is, but equally grave in absolute gravity, we call 2 solids weighing equally, though of mass they be unequal. And basically what that means is that two solids can weigh equally but have different masses, which is false according to Newton's second law. So that's a very interesting point of contention with this piece. There's another definition that is brought up, quote, I call a matter more grave in specie than another, of which a mass equal to a mass of another shall weigh more. And this is a bit of a dodgy translation, so it could mean anything, but the fact that it alludes to something other than mass affecting weight presumably makes it incorrect, but we can't really say for sure. Like, it in specie, I mean, I'm fairly sure the person who translated the piece didn't really have a good translation for that term, because it really could mean anything. And then there is this very interesting axiom. So listen to this. Quote, weights absolutely equal, moved with equal velocity, are of equal force and moment in their operations. Which feels like Newton before Newton, even though it can't be said for sure. Like, kind of force is, you can think about it as mass, or sort of the derivative of momentum compared to time. And so, kind of Galileo alluding to the fact that changing the velocity of something, or of two things that weigh equally, are basically applying equal force, it could be Newton before Newton, but maybe that's not really what he means here, and he's not considering forces in that sort of sense. So yeah, can't be said for sure, but that's all the good stuff that comes out of this piece, other than the volume theories, which is pretty much most of the work. So yeah, after 1613 is sort of when the conflict between the church and Galileo kicks in. It's going to become a main part, or well, not a main part, it's that his works are going to become factors in how he gets charged with heresy and a public arrest and, condemnation by the church. So we'll talk about it in that context, but there's still some works to be talked about. In 1615, Galileo published a revised letter advocating Copernicanism, both as physically true and consistent with a scripture. I don't think it was public at the time that he wrote it, but it became public maybe a couple of years later. And this came only a year before Copernicus's On the Revolutions was banned by the church, and Pope Paul V summoned him and said, you can't publish, or you can't talk about Copernican theory publicly. And he definitely did not listen to him. He didn't stop writing pieces that talked about Copernican theory. Discourse on the Tides utilized heliocentric theory to try and explain tides, although it was faulty. I'll mention a little bit of a long quote that's quite nice and summarizes the matter. Quote, the letter compares the ocean's waves to the disturbances in a vase of water, which moves for three reasons: the slope of the vase, external forces exerted on the vase water system, and the possible acceleration of the vase itself. Comparably, the ocean's tides are due to Earth's terrain, wind currents, and circular accelerations. In Galileo's understanding, Earth's rotation and simultaneous orbital revolution dictate that half of the Earth's rotational arc is in concordance with the direction of revolution, and the other half is opposed to the direction of revolution. He reasoned that by sometimes matching and sometimes counteracting the motion of orbit, positive and negative acceleration is generated that influences bodies of water to rock back and forth, creating tides. So yeah, basically he says the tides happening is basically a matter of contradicting accelerations due to the motion of Earth kind of axially rotating and even around the sun. Galileo also published the Essayer. I think it was 1623 that he published it, which is considered to be important to the foundations of the scientific method. And he tried to cover his tracks later on after the Essayer with a dialogue concerning the two chief world systems, where he's talking about, oh, well, there are arguments for Copernicanism, but then there are also some slightly ridiculous theories against heliocentrism. And that didn't really help his case. His fate was pretty much sealed by that point, and he was summoned again in 1633 and convicted of heresy and was banned from publication. And so, even though he did get banned from publication, his last summative work in 1638 he published his last summative work in 1638. So other than that, I mean, we know Galileo today as a pioneer in astronomical observation, with his observation of Venus's phases, the rings of Saturn, and the mountains on the moon, which he correctly predicted to be about 4 to 5 miles high. I believe sometime in his career as a scientist, he also worked on a pendulum that intended to either swing or half swing every second. I don't remember exactly which one it was, but that was a part of his work at some point. So, yeah, that is a synopsis of Galileo and the work that he did. If you guys enjoyed listening to this episode, I would appreciate a follow on Spotify if you're listening on Spotify, and a subscribe on YouTube if you are listening there. And until the next episode, I will see you all later. Peace.